aspartase that binds PIP3. For the purposes of this talk, the most important thing is that it's a membrane-associated protein. So again, the theme here is that the protein structure was determined. There's a core region of this protein in solution that was found to be highly structured, and then there was a disordered C-terminal tail in solution. So the question is, this as a membrane-associated protein, how does the structure change in the presence of the bilayer? And again, this protein has a lot of implications biologically for cancer, but the membrane-bound structure was not known. So what Hirsch's group did was basically, again, use reflectometry measurements together with simulations to look at the scattering profiles above the surface of the head groups of the membrane. And by, again, a series of contrast matching experiments and simulations, he could fit his reflectometry data to a model for the protein on the surface, again, and actually define a structure, again, through the molecular dynamic simulations that could actually fit this profile that brought that C-terminus into close proximity with the rest of the structure. So, I'm sorry, that extended from the structure. So what his model eventually showed in terms of projecting this on the surface of the membrane is that in the case of this protein, if you look at the membrane-bound state, there's the primary membrane binding domain here is in yellow, and this C-terminus is actually away from it. So the C-terminus seems to swing away from this membrane binding interaction domain, whereas in solution, the simulation showed that this domain actually packed up against the protein and included this membrane binding domain. So the idea here is that the two different states of the proteins